case where f was q and alpha was radical 2. But for now, we'll postpone the proof of this proposition and we'll just take it on faith. But given this, we can try and find inverses of elements in various fields like this. So let's just do 2 examples. If I want to find the inverse of, let's say, 1 plus radical 7 in Q adjoined radical 7, inverse, and write it so one can see this inverse belongs to Q adjoined radical 7. Well, so for this, we can just use the same trick I did before. 1 plus radical 7 is not 0, so I can just write 1 over 1 plus radical 7 and multiply this by the conjugate. So I get 1 minus radical 7 divided by 1 minus 7. So that's minus 1/6, right? 1 divided by minus 6 plus 1 over 6 radical 7. And this way I see that this belongs to Q adjoined radical 7 because Q adjoined radical 7 is elements of the form A0 plus A1 radical 7, where A0 and A1 are in Q. Let's do another example. So example 2, with a slightly more difficult situation. So let's find the inverse of maybe 2 plus cube root of 2 squared. Cube root of 2 squared. And the question is the same, and I write it so that I can see that the inverse belongs to this field Q adjoining cube root of 2. I know this is a non-zero number, so I know the inverse exists in the complex numbers. I just don't know what it is. And I can't really use the conjugate in this case because it involves a cube root, not just a square root. So what do I do? So I know this inverse exists not only in C, but now, thanks to the theorem, I actually know it also exists in this field, right? By the proposition, we know that Q adjoined cube root of 2 is a field, so I know the inverse exists in that field. So write A0 plus A1 cube root of 2 plus A2 cube root of 2 squared with A0, A1, and A2. Rational numbers. So the goal is to find A0, A1, A2. Again, just to summarize, I know this inverse exists in this field because this is a field by the proposition. So everything in this field can be written in that form. So I write my inverse in that form, and I need to find the coefficients A0, A1, A2. So what do I know? Well, I know that if I take this element and multiply it by 2 plus cube root of 2 squared, what do I get? I get 1, because that's the inverse of that. So I multiply everything out and collect like terms. So I get 2a0 plus cube root of 2 squared a0 plus 2a1 cube root of 2 plus this times that gives me just 2a1 plus 2a2 cube root of 2 squared. And these two, let's see, this gives me cube root of 2 to the 4th, which is just 2 times cube root of 2. So that's plus 2a2 cube root of 2 is equal to 1. Collecting like terms, I get 2 plus cube root of 2 squared a0 plus 2a1, I'm collecting like terms with the powers of cube root of 2. So the constants, 2a0, and where's another constant? Here, plus 2a1. So this is the term that does not have any cube root of 2 next to it, plus, now the first power of cube root of 2, so that's going to be 2a1. First power is also here, plus 2a2, plus, now the squares, so that's what remains, a0 plus 2a2 cube root of 2 squared is equal to 1. I can write this side also as 0 cube root of 2 plus 0 cube root of 2 squared. So now by just comparing coefficients, I get the following system of equations. 2a0 plus 2a1, well, that's the coefficient, that's the constant, so that should be 1. This 2a1 plus 2a2 must be 0, and a0 plus 2a2 must be 0 as well. I leave this for you to solve.